The graph of a function f with domain 0 to 4 is shown in the figure. Sketch the graph of the given function f of the absolute value of x. Let's give this a name first. So g of x is equal to f of the absolute value of x. And let's recall that the absolute value of x can be thought of as a piecewise function. The absolute value of x is equal to just x if x is greater than or equal to 0. And the absolute value of x is equal to the opposite of x if x is less than 0. As an example, we do the absolute value of negative 3. We know that's equal to 3, but it could also be thought of as the opposite of negative 3, that is the opposite of x, and where we're using this rule that we take the opposite of x if x is less than 0. Either way, that's 3. Now that might help us describe the graph of g, because if g of x is equal to f of the absolute value of x, then let's describe that in two pieces. That would be either f of x, if x was greater than or equal to 0, and it would be f of the opposite of x if x was less than 0. There I've just applied the definition of the absolute value of x. Now let's refer to the original graph of f. This was y equals f of x. It had a domain from 0 to 4, and that tells me that the graph of g will look just like the graph of f that we just saw up here, that's already been provided, for all of those values from 0 to 4. So as I'm sketching the graph of g, what I know for sure is that it's at least going to have all of these points on it, as well as the graph of f did, just like the graph of f did. But our graph of g is going to include more. So if we're graphing not f, but if we're graphing the g of x, which would be f of the absolute value of x, then we're going to have to include some negative values as well, because the absolute value is going to permit that. So 1, 2, 3, out to negative 4. Now let's think about this f of negative x. If we saw that standing all by itself, we know that when you have a negative multiplier of the argument of a function, that reflects across the x-axis, or the y-axis. Let's see, across is spelled that way. And so we have, for all these values of x that are less than 0, we're going to have the reflection of what we just sketched across the y-axis. That means that for the graph of g, we're going to have this doubled up shape. Let's check that for one point just to see how that works. Let's try finding out what g of negative 4 is. Hopefully that's going to give us a value of 3, actually, if you sketch carefully enough. Let's try g of negative 4. Well, by our definition, g of x is equal to f of the absolute value of x. So f of the absolute value of our x, well, let's evaluate that. F of 4 is what we can simplify that to. And f of 4 can be found on the original graph of f. That was up here at 3. So f of 4 was 3, and that means g of negative 4 should also be 3. And let's skew my line because I didn't draw a very accurate graph. I didn't have my scale quite right. This should be g of negative 4, and that's equal to 3. Similarly, g of negative 3 would be the same as f of 3, g of negative 2 would be the same as f of 2, g of negative 1 would be the same as f of 1, all because the absolute value permits both positive and negative values in the graph of g, even though f's domain was only positive numbers.